Anyway, thank you for attending our event. I'd like to welcome all participants to the 8th webinar in the East 101 webinar series. We are very glad to see you here. If you like our content, we hope you will help us by spreading the word. For those of you who might be new to our company, we are a specialty consulting company focused on advanced processing engineering and flow assurance consultancy services and to the oil and gas, to provide all of these services to the oil and gas industry through process simulation technology. And we were founded in 2003 by engineer Rafael Elias, and we have offices for sales and support, but we are based in Kuala Lumpur. Our services cover transient simulation-based engineering services, as you can see on the screen. Flow assurance services, operational assistance, which includes life cycle operator training simulations and process simulation training. Here's just a list of our previous clients and current clients. For any inquiries, please contact either myself, Zihong, or my colleague Avinash at the numbers and email addresses. And more information is available at 101.com. So through the East 101 webinar series, we hope to cover a wide range of topics, ranging from upstream to downstream and refining, monitoring and surveillance, as well as analytics and AI. It's scheduled to take place every Wednesday from 4 p.m., every other Wednesday from 4 p.m. to 5 p.m. Malaysian time. Today's speaker is Dr. Anuar Hamid, and he is our process engineering manager at East 101. And he has over 10 years of full-time simulation experience in process engineering and operations for offshore and onshore processes, and as well as experience in data science, analytics, and machine learning. Dr. Anuar will be speaking on Reservoir, introduction to Reservoir for chemical engineers, and that's his academic background as well. So without further ado, please welcome Dr. Anuar.
Hello everyone. Good evening if you are in Malaysia, and I appreciate you spending time with us at East 101. It's late in the evening, so hopefully we are all be fully awake. I think it is an exciting topic, especially if you're not coming from petroleum engineering background. So what I'll do first, I'll give some very basic introduction, then followed by looking at how flow looks like in pore scale. And then after that, at the end, we will look at the reservoir simulations, some basics for reservoir simulations. So typically there are two things. If you're not petroleum engineers, if you're sort of the engineers working either midstream or downstream, you're working typically either one of two things. One is typically you'll be given some sort of production profiles. So this typically comes with the oil, gas, and water flow. And then your job typically, if you are process engineer designing the topside facilities, is to make sure that your platform can cater for those flows coming into your systems efficiently and safely. So, for example, this case, this is let me try to put a laser pointer. Okay, so this is a typical, if you were to try to produce oil from a new reservoir, for example, for, from a new field, this is typical, a typical oil production looks like. So initially, once you have your first oil, you have a very steep increase in production rate because you have large pressure, sort of like, just imagine like if you have a tank, if you have a tank, cooking tank or cooking gas tank, if you just bought it, you have like the pressure that's coming out or the flow coming out is very high, mainly because you have high pressure inside your tank or in this case in your reservoir. And then at some point you want to sort of cap your flow at a certain plateau rate, and this is the sort of the maximum flow that if you're a process engineer, again, this is the maximum flow you want to make sure that, say, your separator or your compressor can cater for those plateau or this maximum flow. And then after that, because of you start losing your pressure inside the reservoir and you will have the declining phase, or usually people refer this oil decline curve. And then as you can see, if you integrate these curves, what you'll get is the oil, the total oil you produce from a specific field or specific reservoir. Uh, the plateau can be even higher if you want to make it higher, but it's going to be shorter. The period is going to be shorter, but it can be higher. But the problem is that with that is that you have to make sure your process system, your pipelines needs to cater for that. So there's a sort of balance between how high you want your plateau to be, and then how sort of how far or how wide your plateau that you want it to be. So these usually will come with some economic analysis associated with these curves. So you'll typically get something similar in terms of, say, water flow. So if you've been producing for a long time, and then the water starts to break through, what you'll see is a sudden increase in water flow. Or if you have gas breakthrough or gas cooling, you'll see gas flow will increase as well at the later stage of your production. So this is typically what we get from reservoir engineers from their reservoir simulation analysis or study. The second things that we've been typically work with is, for example, if you are flow assurance engineer or if you are production engineer, if you were to model a well, for example, typically you can do either Olga or PipeSim or Prosper and so on. What you'll do is that at the boundary, at the bottom hole, you need to somehow specify some relationship that relates bottom hole pressure, or I'm calling it here PWF, pressure, well flowing pressure, and relate that to flow, like how much oil or gas coming into the system. So for all intents and purposes, typically for flow assurance engineers or for process engineers, you don't really care what's going on underneath, like upstream of your well, but typically what you'll do in your model or in your study, you'll include this relationship. So hopefully these two things, hopefully if you're sort of in doubt or always wonder where those numbers coming from, hopefully by the end of this webinar, we'll figure out some of the idea associated with these two concepts. Uh, Before moving on, I'm just going to show three sort of main important people in this field. Um, So I think part of the webinar is that if you can name those three people, I'm not sure whether there's prizes for this, but if you can name them, it you'll get congratulations from me. Probably somebody will also send something to you as well. We'll reveal the answer in a short while. If you're a process engineer again, or if you're a mechanical engineer, you typically seen this, or even if you're like a layman, you typically seen this. So what's happening here, like nowadays, uh, if you want to do, say, if you have, say, a car, in this case, an F1 car, and if you want to see sort of the aerodynamics around the car, back in the days, what you have to do is you have to take the car and bring it to a wind tunnel. But nowadays, because of you have the capability to sort of replicate what you have in your tunnel, you can do this. You can do these simulations, or many people refer to it as computational fluid dynamics (CFD), and then you can run many scenarios or studies very fast and cheaply. So because you don't really need the physical things, and you can run many scenarios, run what if cases, and so on. So how people sort of conduct this type of study? Uh, so this is typically the main sort of the workflow, how you are going to do a CFD studies. First, if for example in this case we have a car or F1 car with all the sort of the important features. For example, if you want to capture the wing or the flow, the turbulence or the dynamics around the wings, and then you have to capture that in a 3D model, and then you want to bring that 3D model to here. So here in the middle, what you have is some sort of mesh. Some people call it mesh, some people call it grid blocks, and so on. So what happens is that you want to compute in this case, for example, your wind, your pressure and velocity of your wind around the car. So what happens, you sort of add or put the calculation blocks around the car, and then if you notice, nearer to the car, you'll have a higher resolution. So the grid or the mesh starts to get smaller and smaller, because there are many things happening around nearer to the car, because if you have turbulence, if you have wake at the back of your car and so on, you want to capture that as well. And then by applying some physics, some knowledge of how fluid behaves. In this case, it's just air. How air moves given certain velocity or pressure. We can solve those physics or those equations in this mesh. So basically, you discretize the computational domain, and then you sort of each of this mesh or grid, you perform some sort of calculations, and then you solve for, in this case, pressure and velocity. So what you have down is the aerodynamics around your car. So in order to do this, so two people mainly responsible capturing how fluid moves, either in this case in the atmosphere. So that would be Neville Stokes. Neville, which is a French guy, and then Stokes, a British guy. And then later I'll talk about Darcy, because Darcy is probably one of the most important figure in reservoir engineering and simulation. And also note that for some reason Navi and Darcy came from the same town, from Dijon in France, in Burgundy, France. Yeah, for some reason in 19th centuries, like all this region, they are coming up with all these findings that probably will change for the next century or so. So Navier-Stokes equation, if you read this book, you realize Navier-Stokes equation is one of the things that probably changed the world. If you see number 10, those are the uh, Navier-Stokes equations that relates mainly the momentum and how it relates to pressure and velocity change. Um, so again, if you are working in oil and gas industry, you've probably seen this. This is a fire simulation and dispersion simulations from the NVGL. I think the software called Chameleon KFX. But again, it's the same concept, the same theory, the same math. So what in this case, instead of car, you have an FPSO or your topside model, and then you sort of discretize around the area, and then you, whatever you want to study, you sort of initialize it. And then one of the things that, if you're familiar, in many cases, this CFD, the problem with CFD is that because of the Reynolds number associated with the flows that we are interested in, the Reynolds number are quite high, and then you have, so they are actually in turbulence flow. So for turbulence flow, there are many scales where the turbulence happens. So you need somehow some sort of averaging model to capture the turbulence flow. So in a way, this is not the Navier-Stokes is not fully solved, but there are some averaging model that associated with this kind of analysis. Um, so you'll see why this is sort of related to reservoir simulation after this. Um, so now let's look at pore scale flow, and before going into that, just a brief recap on how we typically find oil, or how we typically exploit oil. So this is the formation of oil, hydrocarbon basically. So on the left you have the deposition of the organic materials million years ago. And then because of this deposition, on your right, if you see, after many million years, you start to have sediment on top of these organic materials. And once you reach enough pressure and enough temperature, cooking will happen. So this is basically the conversion from your organic material to hydrocarbons. So once the hydrocarbon being formed, depending on where you are, you might have migration of oil and gas. If there are enough criteria that fulfill the conditions such a way that the migration of the oil and gas can be sort of trapped and kept in a certain location, then you have the accumulation of oil, gas, and water downstream. Otherwise, your oil and gas formation will just will travel up to the surface, to the maybe to the sea level, for example, and just lose to the atmosphere after that. So again, to recap, there are many sort of criteria, conditions. If you are a geologist or geophysicist, these are the things that you are looking at, whether to see, okay, this is a potential reservoir, oil reservoir or not. You look at whether there's a formation of fault, or the structural dome that sort of contain the oil and so on. And you can see this can be difficult, like because there's only so much you can do in terms of trying to gauge or trying to image what's happening down down underground. So one of the most important things that contributed by geophysicists or geologists is that trying to understand whether you have this fault, or whether you have those conditions that will fulfill the criteria of having accumulation of hydrocarbons. One of the things, if you see here, the important things, if you see this yellow color in each of these diagram, is these are reservoir rock. So these are the ones that where we can take out the fluid efficiently and cost effectively. So again, to recap, like back in the days, I thought there's a pool of oil and gas like in the subsurface, but it's actually sort of trapped in the rock. There are specific rock that can trap this oil, and we call that reservoir rock. Um, so this is me in front of my uni last year. If you see at the back, the building itself is was built by this rock called Portland. So this rock is a limestone rock found in Jurassic Coast, south of England. And if you sort of take just a tiny bit of the rock, probably the size of your ball pen tip, and if you put that under micro CT scan, for example, uh, what you will see is that something like this. So your rock contains all this porous region where you can trap your hydrocarbon, and with that comes water as well. So if you see the black region in the scan is just where the formation of the porous region where you can contain your hydrocarbon. So again, if you look under micro city, these three are the three type of different things. So one is just if you have just pick, if you have bits, and then you sort of pack them properly, and then if you look under microscope and you have what you'll have is like this uh, nicely arranged circles with porous region around them. And then if you look at this type of sandstone, you'll see a smaller but more structured porous region around it. And then this is Portland limestone that we've seen before. And then if you look, the second row is if you do the imaging, this is what I think the guys at Imperial did back in 2012. If you have these stones or this rock, and then if you image it, and then if you do 3D scanning of it, and then you convert that into um, the 3D model. This is the 3D model that you have. So these are basically the pores pieces around the rock itself. So these are the one where the hydrocarbons are. So if you take those pieces and you simulate them, so if you again, sorry, I repeat. So if you take these 3D pore pieces and then you try to run simulation, again the same like what we've seen before, you can solve directly the Navier-Stokes equation, and in this case, because it's not turbulence, so the flow usually very slow in the rock. So what you can do, you can directly solve your Navier-Stokes equation without any averaging of your turbulence, and we call this direct numerical simulations, and you can do that in open form. Open form is just something similar like your ANSYS CFD. And then what you can do, so here the pressure, if you put a pressure on one side and you reduce the pressure, you can simulate the distribution of your pressure across the rock, and then you can also simulate the velocity across the rock. And you can see the distribution of the velocity and the pressure is pretty much dependent on the type of rock that you are dealing with. If you have just a bead pack, you have a sort of more homogeneous displacement in terms of pressure and velocity. Whereas for the Portland limestone, what you'll see is you have this tiny reconnected path, uh, and then the paths are a lot smaller than what you have in the sandstone or in your bead pack. So this is again another type of rock under micro CT scan. I think this is mainly limestone. Mount Gambier, I think it's somewhere in Australia, and you can see this because these are generally carbonate. So carbonate stones, you typically find this in where they have ancient sea back like millions of years ago. So you'll see many carbonate reservoir in Middle East, mainly because all this Middle East region used to be under the sea, under the water. So what you have then the formation of uh, the sedimentation of your like ancient seashell also on, and then they sort of form the rock, and then so it's slightly, so if you have carbonate, it's slightly different. The way you characterize carbonate slightly different than what you would do with normal sandstone. And then if you look at the last rows, what you'll have is that here this is what they call pore network modeling. So this one, I'm just showing this one because you can see clearly sort of where the pores and then the connecting sort of the lines connecting those pores. Um because that will define two things, probably the most important things, whether you have a reservoir that can be exploited economically feasible. So one is whether your rock is porous enough. So it's basically how much of pore spaces divided by the overall volume of your rock. So if you obviously if you have more pore, you can you'll have more fluid inside it, i.e. more oil. And then the other thing, perhaps the most important thing, whether those pores are connected and how easy the fluid to travel from one pores to the other. So this is defined by what we call permeability. Um, and I'll talk about permeability more after this. So this is if you look on your left, this is a test rig by Henry Darcy, the guy that I was mentioning just now. Um, so the original applications or the original purpose of Henry Darcy experiment was something to do with water, because I think he was a water engineer. And then the main problem back then, not trying to exploit oil, but trying to make sure the supply of fresh water, clean fresh water, good. So one of the things that Darcy did was to see, like, if I have a variation in my pressure drop, what will be my flow rate. So what he did, he varied this is a column with porous material, and then he varied the height of the liquid inside this column, and then he measure how much water coming out down here. So what you can do, because now if you have variation of fluid height, that means rho gh, that means different in pressure at the bottom here, and then how that relates to your flow coming out. So if you look, so his results on your upper right, so the third column and the sixth column shows the flow rate, and the meter shows the rouge is your head of your fluid. And then if one were to plot column 3 and 6, what you'll get is a relationship between flow and pressure difference. So in this case, you will see it's pretty much a straight line. Just like V equals to IR, there's another equations that found by Darcy, is that you can somehow relate the pressure difference to the flow rates. Hence, uh, hence the Darcy law that relates the flow of single phase in porous medium. So what you'll have is, if you have Q, if you have Q and if you have pressure gradient, these are just you can use permeability as your proportional constant. So that's it. That's pretty much it. Darcy flow just tells you that in most cases, in 95% of scenarios, Darcy equation works. So if you see that we've gone through several different sort of iteration, trying to understand from how the fluid moves in the pore space. But at the end of the day, this is what we are interested in, that relates an equation that relates between flow and pressure drop. Um, so, however, this is just for a single flow. So, for example, if you just have a water, or if you just have a oil or hydrocarbon. Um, And then I think based on that equation, that sort of answers our how we come up with IPR curves. So again, to recap, just now we've seen IPR curves, this purple line. So this purple line typically given by this Vogel correlations. But before looking at that, just look at this green line. So typically we call this productivity index. So that's basically gives us the as a function of your bottom hole pressure or your well flowing pressure. So let's try to understand how these green straight lines works. So if if I'm looking, if I'm sitting here, my bottom hole pressure equals to my reservoir pressure. My flow is zero. That's that's um, that's feasible, right? That's correct. However, if I start to drop my bottom hole pressure, or if I reduce my well flowing pressure, so I can do that by opening my choke more. What I'll have is an increase in flow. So, for example, if I reduce my bottom hole pressure to around say 1,800, I will get my oil rate to be here is in barrels per day. I get 100 barrels per day, and then I can, based on Darcy law, I can just plot a straight line here. So this is what we call productivity index. So it's just assume a constant or a linear relationship between bottom hole pressure and your oil rate. But what Vogel's, probably many people deal with Vogel's correlation. If you're, say, if you're a flow assurance or production engineers, what Vogel does is simply trying to introduce something that can change the curve a little bit, mainly because in this region, what you have is that if you have large flow, you tend to produce more gas because of, one is probably because of coning, two probably you have more, the gas tend to escape more from the oil solution. So what you'll have is that the gas starts to overtake your oil flow and starts to retard the flow of your oil. So hence you have this thing where you have retardation of oil flow inside your reservoir. And then what Vogel tells you is just that, okay, you have those handles to try to capture those retardation of flow. But at the end of the day, most of the time, you still need some sort of, say, well test data to try to fit this curve and see whether how it looks like, and then yeah, and then come up with either the coefficient for your Vogel equations or the productivity index that you need. I think that covers sort of the idea of this IPR. Again, it's based on single phase Darcy flow, but what people come up with is some sort of handles or knobs to change the shape of your of the Darcy Darcy equations. Okay, so how about multi-phase flow though? So previously we've seen flow relates directly to the permeability. But if we have different phases in your system, there's a tiny correction to your equation where you have another correction factor in terms of, they call it relative permeability. I'm sure you've heard of this. So let's look what is defined by relative permeabilities. So if you look on your right, so on x-axis is what we call water saturation, SW. So water saturation is just uh, how much uh, how much fraction of volume of pores being occupied by water. So if you have, say, SW equals to 1, it means like the whole pores or the whole area of your porous medium occupied by waters, and vice versa. And on your y-axis is Kr, that is the relative permeability. So for the relative permeability, if we are dealing with oil and water system, for example, let's look at the how the relative permeability of water will look like. So KRW is the rel perm of the water. So you can see initially, so if you have initially if you have zero, uh, there's nothing happening between 0 to SWC. SWC is connate water saturation. I'm going to skip what is defined by connate water saturation, but just notice that after the saturation, or after, if you have enough oil volume in the pore spaces, KRW starts to increase. So that means how easy the movement of your water will start to increase, and it is a function of your saturation of water. So here you can see, if the amount of water in the pore spaces increase, the ability for the water phase to move is also increased. Okay, up until one point where you have this thing called 1 minus SOR. SOR is residual oil saturation. I'll define that after this. But before that, let's look at how KRO, the relative permeability of oil, looks like. So, so initially, if you have a low amount of water, it is very easy to move the oil phase because you have less water. But once you start add more water saturations, the ability of the water to move, or the relative permeability of oil to move, will reduce or drops exponentially, until at one point it hits this point, 1 minus SOR, where whatever you do, you cannot move the oil anymore. So this has something to do with the fact that there's interfacial tension between oil and water and the rock itself. So what happens is that, in a simple term, for example, if you if you um, if you smear oil around your hand, and then what happens is that oil starts to stick on your hand, right? So the sticking of the oil on your hand, if you think about the same thing, what will happen on the rock is that the oil starts to stick on the wall of the rock, and then the amount of the oil that left, or residual oil we call it, is called SOR here. So whatever you do, you cannot remove that. So I'm sure you've heard of EOR. EOR is enhanced oil recovery. So the idea of EOR, one of the main idea is, how can we change this SOR? How can we sort of strip some of the oil that's sort of trapped on the wall rock, on the wall of the rock, and then how can we sort of strip it and then sort of produce it. So just again, if you remember our analogy, if you have oil on our hand, one thing we can do, we can use soap. So when you use soap, basically you will try to change the interface between oil and our hand, and what you do is you change the interfacial tension between those two. So this is the same thing. Typically, one of the famous EOR method, which many people in at least in the Europe is trying to do, is to use foam. So basically, you can imagine uh, it's like push pumping sort of a chemical that looks or at least behaves like soap and try to strip all this oil. So that is one of the sort of the purpose or the objective of your, i.e. to to increase the residual oil that trapped in your rock. So again, at the end of the day, like if we are dealing with say reservoir simulation, these are the things that very important that we will need to capture in reservoir simulation, which we will look after this. Um, so how do you measure these relative permeabilities? If you look on your left, is that when people do exploration or exploration wells, when they drill and they bring up the sample, the core sample, and then they will send it to the lab. And in the lab, they will try to replicate the flow of oil and water. So here you can see water and oil being injected, and then from that on your right you can see the resulting permeability curve. So this is purely, I would say, empirical, where we just take a sample and then send it to the lab, and then we will use these curves inside our reservoir simulation after that. Um, yeah, I think we've covered pretty much all the sort of the basic or the important stuff that you need to do before we move on into reservoir simulations. Um, just to recap, on your left, what we looked before is the pore scale. We are mainly looking at the scale of micrometer to millimeter, and then next after that we are dealing with core sample perhaps. So we are looking at either centimeters, several centimeters, and then on your most right hand side is your the field scale, which is what we are interested in when we want to do reservoir simulation. We are dealing either in 100 meters or kilometers. So you can imagine from pore to field scale, there are certain things we have to capture, certain things we have to ignore in terms of physics or in terms of things we want to model. So before that, I guess if since many of us are not from reservoir engineering background, I would just want to compare and contrast what we have in terms of transient modeling from your reservoir to your pipeline up to your topside process. So in terms of reservoir simulations, the governing physics, I think we've covered this one, is mainly looking in terms of multi-phase flow in porous media. Then we are looking in 3D spaces instead of 2D or 1D. And then the flow inside the reservoir, we are looking at in terms of meter per day. So if you have a fluid front, and then because of the area of the reservoir is very big, even if you wait until tomorrow, the front of the fluid will only move for maybe a couple of meters or couple of feet. Uh, in terms of time step, if we were to do reservoir simulations, we are looking at days, and the typical software that we need, typically coming from Schlumberger, Eclipse, or if you are from North America or from Canada, you typically will use CMG. Uh, So, and compare that to what we are used to in terms of flow assurance and process simulation. For flow assurance, we are mainly looking at 1D pipelines, whereas in process simulation, it's basically 0D, everything is 0D. Everything sort of being lumped together. If you have a tank, it's a tank, a lump tank. There's no distribution across the tank, for example, in most cases. Typical fluid velocities, we are looking around maybe 1 to 5 meter per seconds in the pipelines. Same goes for your process simulations inside your pipes, because that's governed by your either erosional velocity, or your flow assurance requirement. In terms of steps, if we are using Olga, we are typically dealing with minutes instead of days. Whereas if we use simulations, we are dealing with maybe fraction of seconds to seconds, depending on what sort of transients events are happening. Sometimes we need to capture the fast events like the opening of a certain fast-moving valve. Then we need to cut down our time step a little bit more. And then the other software for flow assurance, again by Schlumberger, is either Olga and Leader Flow. I think I'm just putting Leader Flow such that to show we have some choices, but probably we will need Olga most of the time. For process simulations, we typically use either HYSYS and Schlumberger now come up with Symmetry, which used to be VNG Sim, and Icon if you are coming from Petronas. So one of the things that many people wonder, okay, can we simulate everything down from reservoir to pipeline to top sites? These are one of the things that you have to keep in mind, is that the time step requirement are completely different from one domain to the other. So those are the things that you have to remember, and typically will bring problems in terms of computations. Um, so this is a typical reservoir model. So I want to highlight two things. Notice you have blocks, grid blocks, similar to what we had before in computational fluid dynamics. But these blocks, instead of just air, these blocks needs to represent rock. So this block, each of these blocks needs to be assigned with one, porosity value, two, its permeability values, as well as if you have relative permeability values that are probably different from one region to the other regions. Uh, and then also another things to note is that you can, these blocks are very big. So for example, if you are dealing with say 10 kilometers of reservoir, you can see if I have like 100, I don't know how many blocks, maybe hundreds or 200 grid blocks here, you can see each size of your block can be very big. So probably the size of your room you're sitting in, or the size of building you're in now. So you can imagine how that might pose another challenges, especially when we're dealing with this very big model. Um, so here the colors indicate the porosity. So red would be higher porosity rock. And then those are the wells that where you want to place your wells. So many people are confused with two things. One, because there are things that different people refers to different things. But I would want to make differentiation between reservoir modeling or characterizations versus reservoir simulations. So reservoir modeling or characterization is mainly done by geophysicists or geologists. So this is just coming up with this, we call it static model. The reservoir itself, like where are the faults, how the porosity or permeability distributed across your reservoir, where are my aquifers and things like that. So this, many people refer this to reservoir modeling. So you can see in this diagram, in order to do reservoir modeling for geologists or geophysicists, they will look at things like your seismic imaging, your well test data, and then try to see whether you have different type of rocks across your reservoir, and come up, and then starts to populate those model with grids that contains your rock properties in terms of porosity and your permeability. And then once we've done that, and then with that model, then you pass it to the reservoir engineer to be used for reservoir simulations. So only then we take that model, physical model, static model, and then starts to populate where uh, the oil, gas, and water, and then see and determine where we want to place our wells, and then see how much flow that will come out of those wells. So based on those simulation, flow reservoir simulation, then you would have your production profile and so on. And so, for example, if you still remember our production profile, it has the plateau. So if you want to increase that plateau, you might need to add more wells, for example. So depending on your strategy of exploiting those reservoirs, sometimes you might want to keep the plateaus for longer. Then you don't have to have as many wells that as you need. Then you just place the wells accordingly wherever you need. Um, so I guess another things to address is mainly how you characterize the fluids. If you're a fluid assurance engineer, I'm sure you're familiar with this. In Olga, what you'll do is you don't have the luxury of having on-demand flash calculations, so you can't just keep asking it to flash. So what you'll do, you characterize your fluids and then generate a table that defines a certain boundary in terms of pressure and temperature, and then what are the sort of associated uh, fluid properties with those. And then you put that in the table, and then from Olga, you refer to that table based on your location of your pressure and temperature. It will just read off those tables. So that is what we call in Olga. You probably just say it's PVT table, but the other method you can do is you can use black oil model. So basically, you put some sort of correlations that will define, say, if you have a barrel of oil underground, what will happen if you bring up over the ground. So you have to define it in terms of uh, the shrinkage of the oil volume, as well as how much oil, how much gas you are producing. So typically, in reservoir simulation, we deal a lot with black oil simulations. So if the software for that, for Eclipse, there's a sort of a subset of Eclipse. It's called Eclipse 100, or for CMG, it's called IMAX. So this only handles black oil simulations. Whereas if you need to use PVT table, in this like reservoir simulation lingo, they call it compositional reservoir simulations. You need to use Eclipse 300 or GEM by CMG. Um, and the way it works pretty much similar to how you use your PVT table in Olga. Uh, so then once you have your reservoir model, as a petroleum engineer, to perform reservoir simulations, we define all these things, where you want to place your wells, the definition of water oil, gas oil contacts, your rock properties, your relative permeabilities, your fluid properties, and things like that. And then you will simulate it to produce your oil, gas, and water production profiles, like we've seen in the first slides of this webinar. Uh, so there are different exercises that typically you will need to do, because there's a lot of uncertainties with this reservoir modeling. So if you are a geologist or geophysicist, you have to do a lot of simulations. They call it Monte Carlo simulations, where you start to say, okay, if I'm not sure the fault is here, what happens if I change different model of my faults or the location of my aquifer, for example? And then in order, you have to run many cases, and you will output, you will give results of, for example, the standard oil originate in place. So to come up with that number, you have to run many Monte Carlo simulations, and then come up with sort of the PDF, the probability density function associated with the stoic. Similarly, if you are doing reservoir simulation down at the bottom, you don't do one simulation because there are many uncertainties. For example, the probabilities, your curve might look slightly different. Your endpoint in terms of the residual oil may be different. Then what you want to do, you want to sort of uh, change those or run many cases such that you will report probability instead of one number. So typically they will report that in terms of P9, P50 or P10, like where in terms of if you have a Gaussian-like distribution, where are those locations in terms of oil that will be produced from those fields or reservoir. And then I think this is the last slide. I mentioned that the fact that typically there are many computational overhead costs associated with running reservoir simulations. The things that many tools consider. So basically, your rock, your grid usually might be smaller. And what you want to do, you want to lump them to a bigger grid block. In order to do that, you need change your iterative frequency or other things that you change such that you can replicate or reproduce find your oil or gas simulation that would be produced from your fine model. Uh, so this is what we call upscaling. Uh, with that, I think I would end my presentation. Thank you again for your time. I hope that was not that boring. I'll pass back to Zihong. I think Zihong is having a bit of problem with connection, so I'm going to take questions if anyone have questions. And I'm
Hi,
going to give
Anwar.
liberty for you guys to talk. Yeah, you don't need to type if you want.
Okay. I have a question. It was a very interesting presentation, and I'm a full assurance engineer from Jakarta, BT7 Indonesia. I have a question related to the reservoir modeling that you explained before.
Yeah.
As per my understanding, it was more about like oil reservoir. And my question is, do we have any kind of difference between oil and gas reservoir, like in terms of permeability and also in terms of, you said like I mentioned something like residual oil, but do we have also something like residual gas or?
Yeah. So I think I covered mainly two phase flows. So if you have three phase, which you would have in many cases, is you'll have another relative permeability curve for gas. But it's gonna be the reason I didn't show because it's gonna look hideous because there are many uncertainties related to that, and what happens is that many people use different type of correlations. One of the popular correlation is called stone 2. So yeah, you sort of have the same concept where you have the gas also, you can have different relative permeability. So that is one. I also want to cover the other things, mainly in terms of the difference between gas reservoir and oil reservoir. If you're mainly if you're flow assurance or production engineers, typically, so there are two ways to model the reservoir, right? Either you model it full-blown reservoir simulation, i.e., you create a 3D model, populate your reservoir with your rock properties and see what will come out. So that is one. The other way to do this is purely by mass balance. So what you'll do is that, okay, I know what's the original material inside my reservoir based on a certain pressure. If I deplete this pressure, how much will come out? And I do sort of accounting, like, okay, I've already produced this much. This fluid is still underground, then I can do some sort of material balance. For all for gas reservoir, that is easy because if you can imagine your cooking gas cooking tank, uh, so it's easy because you can characterize it pretty much easy, and then you can use things like MBEL by PETEX, by Petroleum Expert, and then include that as part of your study for your fluid assurance, for example. But for for oil reservoir, there are certain difficulties because the analytical solutions or the things that you can calculate by hand is not that easy. So you can't, in many cases, you can't use things like MBEL to model that because what you're doing, you're treating your reservoir as a 0D model. It becomes a tank model, and you're trying to do simple calculation based on that. So in summary, the main differences, I don't think in terms of the rock property, it will be different. Uh, but in terms of how easy you can model certain stuff, it will be different if you're dealing with gas or oil reservoir.
Okay, thank you for the explanation.
Thank you. Thank you for your questions.
Dr. Anuar, we have a question in chat
Yeah.
from Senapati or Saroj. Good presentation. Can you please explain P10 or 50 or 90 in the profile? Which one is taken for surface design?
So P10, P50, P90 is just, if you still remember your bell curve. So P50 will be in the middle. P10 is sort of on your left or on your right, depending where you're looking from. And then the other extreme would be P90. So these are used for the oil company to decide whether certain field is feasible to be developed or not. So for example, okay, I have 90% confidence that the reservoir will produce this much. Uh, but in terms of the one that will be taken by surface design, I think that depends on the talk or discussion between the the surface engineers and the subsurface engineers, which one to be used for your design. So, for example, you might want to design your water handling system to be slightly bigger, for example. So that one would be, I think there will be different analysis just for that. But P10, P50, P19 purely for decision making, whether to like how confidence you for this field to be developed or not.
I see. Thank you, Dr. Anuar. I hope I answered the question. We have something from Sukrut. Uh, Thanks for sharing the info. Is there any guiding principle for considering black oil model or compositional model for estimation of the properties? Which one yields a robust analysis? Thanks.
I think 90. I'm going to put a number. 95% of the time you can get away with black oil model. The reason being, even though you are not sort of nailed down the property of the fluids properly, it doesn't really matter because there are many other things that are uncertain. So, for example, your location of your the porosity or your permeability distribution might be wrong or not accurate in the first place. So, in many cases, black oil model, you can get away with black oil model. The only reason why you might want to use composition if there are any things that you specifically want to see. So for example, if you want to do miscible flooding, for example, so for that, there would be different miscibility. For example, if you want to do CO2 injection, there might be different miscibility as a function of your pressure and temperature. Then you might not be able to capture those phenomena specifically using black oil model. Only then you would go for compositional model lah. But to be honest, I never seen people use black oil model for their day-to-day work, except if you deal with special reservoir. So for example, in the Canada, if you're working with heavy oil, with tar sand, you probably need to say, for example, to include thermal calculation inside it. So then you use different nations that would capture those phenomena. As it is, if you're dealing with normal reservoir, I don't think you would need, or normal fluid, I don't think you would need compositional model. But bear in mind, for the even if you're dealing with black oil model, you might have things like, so for example, if you are dealing with carbonate, you might want to use dual porosity model for your rock, for example. So those are the things that is different, but that has nothing to do with black oil model. In terms of the estimation of the properties, again, many of these black oil model are correlated to a certain correlation. So for example, you have standing, standing is the most popular one. I think that was regressed mainly for North America oil. And then you have Glasso, which is regressed for North Sea oil. So those are the things that probably more important for you to understand how they come up with those properties when they define the black oil model. And in some cases, you might need to do regression yourself and put more definition in terms of curves being defined in your model based on your lab measurements. That's all my answer, Leon.
Oh, that was a very detailed answer. Thank you very much, Dr. Anuar.
Thanks.
We have something from Muhammad Hamza. Can you briefly explain water breakthrough occurrence during production and what might be going on in the reservoir? Thank you for sharing.
Okay, so if you are dealing just purely, say, if you produce the oil, so if you still remember from the from our relative permeability curves, water is always there. Water is always there, but if you have many oil inside the porous medium, the oil cannot move because we have this thing called water conic. So water will sort of stick in the pores, but it cannot move. So if you just produce the oil, you don't have water breakthrough because the water cannot move purely because the relative permeability is zero at that point. But typically, what happens to prolong the reservoir production time, because if you take a fluid without substituting it with different kind of fluids, what happens is that you will start to deplete the pressure underground very fast. So just imagine if you have a kilometer area of oil initially there, and then if I take it out, then your volume is still the same, but your fluid sort of supporting this volume keeps on decreasing as we produce. So what happens, you need to replace those fluids. And how you do that? One is either you have a water injection or you have active aquifers, i.e. the naturally occurrence water reservoirs surrounding the oil reservoir. So water breakthrough will happen when those oil at the back. So for example, if you inject water as part of your pressure maintenance exercise, what happens is that at one day you will start to see that water in your production well. So again, to repeat, typically in the reservoir you have two types of well. One is production wells, that's where you produce your oil, and the other one is for pressure maintenance. So it can either be gas injection or well injection typically. So for water injection, when you inject it, at some point it needs to be produced because it's there, and then it will start to overtake the flow of oil. So that's when you'll have those water breakthrough. So once you have water breakthrough, you know it's almost game over lah, in terms of the amount of the water will come in. You know it will keep increasing. You will not say once you have water breakthrough, it's not going to be stagnant for a while and then increase again. You know it's will going to be keeps increasing because it's just sort of the you just get the water at the back now at the your production wells. That's all the answer that I have for Hazrina.
I see. Thank you
Zion,
very
do
much.
you have any other questions?
Does anybody else have any further questions? And
We can keep repeating if you don't answer again.
Yeah. Yeah, I think Zirong, I think it's already 11, so it's 16 past 5. I think we should let everyone to resume whatever they were doing, or probably go back home, have a nice dinner. It's raining outside, I think, at least inshallah. For myself, I hope you guys had a good time or you learned something new. If not, blame me, don't blame Zuham. And with that, from myself, that's all that I have. Thank you for your time. I think we can stop now.